Hello everyone, and welcome to the third chapter of our Chemistry O-Level Lessons series. This chapter is called Methods of Purification, and here we have the learning objectives of this chapter. The topics of this chapter are listed in the description below, along with their timings and chapters. Using those, you can watch specific parts of this video, the topics of this chapter. So, in this chapter, we're going to learn to describe the difference between pure substances and mixtures. We're going to state the effects of impurities on melting points and boiling points, describe the methods of purification using solvents, filtration, evaporation, crystallization, and distillation, simple and fractional. We're going to learn to suggest suitable methods for purification, given information about the substances involved. We're going to learn to describe paper chromatography and interpret chromatograms, including comparisons with known sample and the use of RF values. We're going to learn how we can explain the need to use locating agents in the chromatograms of colorless compounds, deduce from the given melting and boiling points the identities of substances and their purity, and explain that the measurement of purity in substances used in everyday life, like drugs and foodstuffs, is very important. So many foodstuffs have special food additives like colorings, preservatives, sweeteners, etc. Food scientists regularly check food to make sure that only the permitted additives are present and in the correct quantities. Chromatography is a very useful and sensitive technique for testing such additives, especially artificial colorings. We're going to see what paper chromatography is and learn how we can do it in this chapter. So, without further ado, let's dive into this chapter by first understanding pure substances and mixtures. So, often we regard a pure substance as something which is clean and unpolluted, and an impure substance as its opposite. However, in science, purity is more than just being clean and unpolluted. Polluted seawater is obviously impure, but to a scientist, so is clean, fresh seawater. So, in science, we say that a pure substance contains only one type of substance, that is, one type of atom or molecule. So if water is to be pure, it needs to have only H2O and no other atom or molecule of any other substance. Only H2O. So pure water is a pure substance, but seawater also contains dissolved salts, as well as other dissolved substances which are referred to as the impurity. And even in clean fresh water, there's still some dissolved salts. That's what we're talking about. That it's still impure, even though we can drink it. So remember, we only call a substance pure in science when it contains only one type of atom or molecule. For example, water can only be pure in chemistry if it is made up of only one type of molecule, which is the H2O molecule. If it contains some other molecules as well, like some dissolved salts, like sodium chloride, as a salt, then it will not remain pure. It will become impure. Even though we can drink with it, even though it's not harmful to us, but still, in chemistry we will call it impure. Normally we call something polluted and something unclean as something that we cannot drink or that is harmful to us. But in science, it's more than that. A pure substance contains only one type of substance. So, scientists need pure substances to study their properties. Food and medicines have to be tested for purity before they are sold, as any impurity in them could be harmful or poisonous. So in the electronics industry, microchips have to be made from very pure silicon. Any impurity in the chips can greatly reduce their effectiveness. So in the previous chapter, we read about melting and boiling points and the states of matter and their changes of state. In that we read that a pure solid has a fixed and exact melting point. Presence of an impurity lowers the melting point and causes the substance to melt over a range of temperatures. An example of this is the addition of salt to ice. Like I said in the beginning, seawater is something like the same. But ice is a solid. So pure ice melts exactly at 0 degrees centigrade. But when salt is added, it lowers the melting point to values between -5 degrees centigrade to -25 degrees centigrade, depending upon the quantity of salt added. So This is the reason why in cold countries, salt is spread on icy roads in winter to melt the ice. The melting point lowers, and so the ice melts at a lower temperature than its actual melting point. So any impurity in a solid would lower the melting point of that solid. With liquids, any impurity raises the boiling point. A pure liquid has a fixed and exact boiling point. For example, water boils at 100 degrees centigrade exactly. However, when salt is added, it raises the boiling point. And remember that a pure liquid would have a fixed and exact boiling point only at atmospheric pressure. The pressure can change the temperature as well. The same is for the solid. A pure solid would also melt at its melting point, exactly at its melting point, under atmospheric pressure. So, mixtures do not have exact properties as their compositions can vary. Because of this, they do not have fixed melting and boiling points. By mixture we mean a mixture of two different substances or three different substances. So, that mixture is obviously going to be impure because it's not made up of only one substance. And so, that is why it won't have exact properties because its composition can vary. Every time we make the mixture, the composition can vary. And so because of this, they do not have fixed melting and boiling points either. For example, petrol is a mixture and has a boiling point within the range of 35 degrees centigrade to 75 degrees centigrade. This is how we tell the temperature of mixtures. We tell a range, not an exact boiling point. Like we know that ice melts at exactly 0 degrees centigrade. But with mixtures, we don't say that. We don't give an exact temperature. We tell a range of temperatures within which it will be likely to boil or melt. Candle wax is also a mixture and has a melting point within the range of 50 degrees centigrade to 60 degrees centigrade. Okay? So, mixtures are formed by a physical change only. Because of this, they are easy to separate into pure substances. So this process of separating mixtures into pure substances is called purification and can be achieved by simple physical methods like dissolving, filtering, evaporating, distillation, and chromatography. These are the different methods that we're going to look at one by one. So the first method that we're going to look at, the first method of purification that we're going to look at is the dissolving, filtering, and evaporating method. This technique is only suitable for separating a mixture of solids which behave differently in a particular solvent. Solvent means liquid. So, in this we need a mixture in which one solid must be soluble in it and the other solid should be insoluble in the solvent. For example, a mixture of salt and sand. So, when water is added to this and the mixture is stirred, only the salt dissolves, but the sand remains in it. The sand can then be removed by filtration. We saw dissolving, filtering, and evaporating. So, we filter the sand as it collects as a residue in the filter funnel. So, here is what happens. We have the mixture of liquid and solid. The liquid contains salt as well, but it's absorbed, so it will move with the liquid. The sand, it is passed through this funnel, and there's a filter paper in the funnel. It is a semi-permeable paper that separates solids from liquids. So the liquid passes and is collected in a beaker below, and this is called the filtrate. And the sand that is collected in the funnel is the residue. These are the solid particles trapped by filter paper. So when the liquid passes through the semi-permeable paper, you can see that the orange molecules here shown are the sand molecules, and these green ones, they are the water molecules, and because they're smaller in size, they pass through this filter paper, and these bigger molecules of the sand remain on top. So through this filtering, we get the sand. The sand is removed and we can then wash it with water to make sure that it is clean. Now what we are left with is the salt solution, water and salt. We want to separate the salt from water now. And to do this, the solution can be evaporated to leave pure salt crystals in the evaporating dish. So here we have the evaporating dish. Here we have the mixture. What we do is that we place it on a Bunsen burner. This is a gas burner used to heat and sterilize. We have a tripod platform which supports and holds the glassware. We have a gauze mat which supports the container and evenly distributes heat. We have the evaporating dish which is used for evaporation of liquid. So if we place the liquid on a low heat, there will be a slow evaporation. And the slower the evaporation, the larger the crystals. So we evaporate water from the solution, and in the end we are left with the salt crystals. So natural evaporation would produce the largest crystals, but it takes too long, so gentle heat is used. Care should be taken not to evaporate to dryness, which could damage some crystals by removing their water of crystallization. So the water of crystallization is important for crystals. So this is how we then get the crystals, salt crystals. So if we have sand and salt, and one of these substances is soluble in water and the other is not, we use the dissolving, filtering, and evaporating method. We dissolve the mixture in water. One solid is going to get absorbed in this water, but the other would not be absorbed. So we would use this method to separate the two solids, sand and salt. Suitable apparatus for carrying out this technique is this. When a solid is dissolved in a liquid solvent, a solution is produced. If this solution is heated, some of the solvent evaporates. So when the hot solution is allowed to cool, some of the dissolved solid reappears as pure crystals. And this is known as crystallization. So let's talk about crystallization for a moment and understand this. So when a solid dissolves in a liquid solvent, a solution is produced. If the solution is heated, some of the solvent evaporates. So when the hot solution is allowed to cool, some of the dissolved solid reappears as pure crystals. So this is called crystallization. It is useful when the impurities of the substance are also soluble but remain in the solution as it cools. Crystallization is used to purify sugar and fertilizers like potassium nitrate. Crystallization can also be used to purify solids just by melting them. So when the hot molten liquid cools, crystals form. The first crystals to form are always very pure, and they can be separated by filtration before the rest of the molten liquid cools completely and becomes a solid. Microchips are made from very pure silicon. To obtain such crystals of silicon, it is necessary to heat the silicon to its melting point at 1410 degrees centigrade. The molten silicon is then cooled slowly so that pure crystals are formed as the liquid freezes. The first crystals to appear are very pure and are filtered out to be used as microchips. This technique is called crystallization, but it doesn't use a solvent. Like I said, crystallization can be used to purify solids just by melting them. So this is what we do here. We melt the solid, and then when it cools, it produces crystals. Now, seawater is a mixture of mainly common salt and water. In the hot countries of the world, seawater is allowed to flow into large flat salt pans. Here, the hot sun evaporates the water, and so this is called solar evaporation. The seawater therefore becomes more concentration in salt and forms a brine solution. As the evaporation continues, the brine eventually becomes a saturated solution, and further evaporation causes the salt to crystallize. It is then removed by filters or scoops. Through solar evaporation, very big crystals are formed because it is slow. So let's see the meaning of some common words that I'm saying. Soluble. Soluble is a substance that will dissolve in water. Okay, and insoluble is a substance that will not dissolve in water. A solute is normally a solid which dissolves, and a solvent is normally a liquid which does the dissolving. Like water in this case is a solvent, and salt is a solute. Salt is a solid that dissolves. It gets dissolved, whereas the water is a solvent which does the dissolving. It is in which the solid dissolves. Solution means solute plus solvent. Residue means insoluble solid which is trapped in a filter funnel. We read before. Filtrate is a solution that passes through a filter funnel, and a crystal is a solid that reappears from the solution. Okay, so this was a quick revision of what we just read here. Now, let's see the second method of purification, and this is decanting and centrifuging. These are used as alternative techniques to filtration. Decanting means carefully pouring off the liquid and leaving the undissolved solid. For example, sand at the bottom of a beaker. It is quicker than filtration, but separation may not be so effective. So this is decanting. We use a glass rod to assist decantation, and here we have the liquid separated from the sediments. Then we have centrifuging. Centrifuging is useful for separating fine insoluble solid particles from a liquid. As these fine particles are light, they are held in suspension throughout the water and only sink to the bottom very slowly. So decanting will be impossible. They are called suspensions. Some examples of suspensions are clay particles in water, chalk particles in water, and blood cells in plasma. Here we can see chalk particles in the water. So in the centrifuge, an electric motor causes the test tubes to revolve at high speed. This flings the solids to the bottom of the test tube, where they collect. So the clear liquid can then be decanted off. So a mixture of sand and water can be easily decanted because it is heavier than water, it will sink to the bottom. But some suspensions like clay particles in water and chalk particles in water and blood cells in plasma, they are fine particles, and because they are light, they are held in suspension throughout the water and only sink to the bottom very slowly. Sand, on the other hand, is heavy, so it sinks faster, whereas other suspensions are light, so that is why we use centrifuge to revolve them at high speed so that they can fling to the bottom of the test tube. Then we can decant the clear liquid off. Okay, then we have the separating funnel. This is also another technique. So this technique is quite different from all the other techniques because it is used to separate two liquids which do not mix together. Two liquids, not solids and liquids. Two liquids which do not mix together, for example, water and oil. Such liquids are said to be immiscible. Immiscible means the ones that do not mix. The liquids that mix are called miscible. So the lighter liquid, which is the oil, collects above the heavier liquid, which is the water. We have a tap, like this is stored in a tap. So when we open the tap, the water is run out and the tap is closed just before the oil reaches the bottom. So separation is never entirely complete because it's not that accurate as well. We have to do it ourselves. There might be some oil droplets that enter the water in the flask. But still, this is also a quick method for separating two immiscible liquids. The separating funnel. After this, we have sublimation. In the previous chapter, we saw what sublimation is. When a solid turns into a gas directly, that is called sublimation. So this technique is limited as only a few substances such as ammonium salts, iodine, and naphthalene sublime. It is only used on those substances that sublime. Sublimation is the process of changing directly from a solid to a gas, usually on heating, or from a gas to a solid without any liquid phase. Through sublimation, we can separate a mixture of two substances, in which one is a substance which sublimes and the other is not. So, it can be used to separate a mixture of ammonium chloride and sodium chloride. Ammonium chloride in this sublimes, whereas sodium chloride doesn't. So, the mixture is placed in an evaporating dish with inverted glass funnel over the top. So here you can see, we have a china dish and we have the inverted funnel over the top. This is then gently warmed. The ammonium salt inside changes into a gas and cools back to a solid on the cold glass funnel. So it is called the sublimate. The sodium chloride remains in the evaporating dish. So this is how sublimation is done. After this, we have a very interesting process, an interesting method of purification, and this is simple distillation. This method is used to separate a pure liquid from a solution. For example, water from salt water. Salt water is a solution, and the pure liquid that we need to separate from salt water is water. So simple distillation is used to separate a pure liquid from a solution. Here, as you can see, this is the apparatus we used. The flask here contains the liquid, the solution, the salt water. This is heated, and when the solution boils, steam is given off. This steam is cooled down and condensed in a Liebig condenser. This is the Liebig condenser. The Liebig condenser consists of a jacket of cold water, with the coldest water entering at the bottom of the jacket and circulating out through the top. The condensed water is called the distillate and is collected in a receiver. This is the receiving flask. So, the water which collects in this way is very pure, as all its impurities are left behind in the flask. That is why it is called distilled water. The thermometer here indicates the temperature at which the water vapor distills over, which is 100 degrees centigrade, as we all know the boiling point of water. The thermometer is positioned with its bulb next to the side arm so that it records the temperature of the steam as it enters the Liebig condenser. In order to maintain even boiling with not too much bumping and bubbling in the flask, anti-bumping granules could be added to the salt water. So this is simple distillation. It's very simple, as you can see. The solution is boiled and then the steam given off is condensed. So the condensed water is very pure. It is called distilled water. So this was simple distillation. I hope you've understood it. So now we're going to move ahead onto fractional distillation. Quite similar to simple distillation, as its name implies as well, but this is a little different. Fractional distillation is used to separate two liquids which dissolve in one another. Previously we saw the separating funnel, but that used to separate liquids which were immiscible, that is, which couldn't get dissolved into another. But fractional distillation is used to separate liquids that are said to be miscible because they mix completely to form a single layer. So, the separation in fractional distillation relies on the difference in boiling points of the two liquids. For example, water and alcohol are miscible. They have boiling points of 100 degrees centigrade and 78 degrees centigrade respectively. Of course, 100 degrees centigrade is of water and 78 degrees centigrade is of alcohol. So, here we have the apparatus of fractional distillation. It's quite similar to the previous one, except for that we have a fractionating column here above the distilling flask. And again, we have the Liebig condenser and everything is the same. This fractionating column used is normally packed with glass beads or some other unreactive substance. So, when the flask is heated, the vapor coming off from the mixture will contain both ethanol and water molecules. But because ethanol has a lower boiling point compared to water, it will be richer in ethanol molecules. So what happens is that at first, this vapor condenses on the cold fractionating column because the boiling points of both the liquids hasn't reached yet. But as this fractionating column warms up, molecules in the vapor state rise further before condensing. Of course, it would rise and then it will condense back down. And as the fractionating column's temperature would rise and get closer to the 78 degrees centigrade, the vapor would rise further and further. As we go up the column, the temperature becomes lower and so the proportion of the ethanol molecules with the lower boiling point increase. When the temperature at the top of the column reaches 78 degrees centigrade, the molecules of ethanol can survive as vapor and these pass over into the Liebig condenser. Previously, the boiling point hadn't been reached, so the ethanol molecules couldn't survive as a vapor and they used to fall back down, condense back down. But as the temperature reaches 78 degrees centigrade, the molecules of ethanol can survive as vapor and these pass over into the Liebig condenser. Water molecules are left behind because they have a higher boiling point and condense in the fractionating column and fall back into the flask. This continues until most of the ethanol is boiled off. But when the temperature at the top of the column rises to 100 degrees centigrade, water passes into the condenser. It can be collected in a different receiver. So, in this example, complete separation is not effected and the ethanol distillate will contain some traces of water. These final traces of water may be removed by the addition of a drying agent like anhydrous calcium chloride, which is then filtered out to leave pure ethanol. So, this was fractional distillation. It is a very useful technique for separating crude oil, which by itself is a useless mixture, but is made up of individually very useful miscible liquids such as petrol, paraffin, and diesel. These are called the fractions of crude oil. So we separate crude oil into these fractions by the fractional distillation. Fractional distillation can also be used to separate the components of liquid air. So this was fractional distillation. So this brings us to the last method of purification, which is paper chromatography. Now, paper chromatography is a quite different technique compared to all of the ones that we've seen so far. It is quite different and it's very interesting. The name of this technique comes from the Greek word chroma, meaning color. It was first used to separate colors, pigments, and dyes. But nowadays, it can also be used to separate colorless substances. So the principle involved in this depends upon the relative solubilities. In paper chromatography, the piece of paper used, like most paper, contains water loosely combined with the cellulose of the paper. So if a dye is put in small spots at the bottom of the paper and another solvent is soaked up the paper, the solutes present in the dye dissolve to different extents, like this. It's not actually like this. This picture has been cut. At first, it moves up here and then it goes up to here. It looks something like this. As the liquid soaks up, the dyes move upwards. So, what happens is that the solutes present in the dye dissolve to different extents. Some are more soluble in the mobile solvent moving up the paper. Others dissolve better in the water trapped in the paper and therefore do not travel very far up the paper. This difference in solubility allows the different pigments in the dye to be separated. So, this is how paper chromatography works. Chromatography, although a simple technique, has many important applications besides identifying color pigments. In medicine, proteins, which are complicated molecules, may be identified using chromatograms. Here, the building units of proteins are amino acids, which, like pigments, travel different distances with solvents. Although amino acids are colorless, they can be sprayed with a liquid which reacts with them to make them visible. We call such liquids locating agents. Then hydrogen spray is a locating agent which can react with the colorless amino acids to form a purple stain. Other substances produced by the body, such as urine, can also be analyzed by chromatography. So this is what paper chromatography is. What happens is that a dye or any other substance is put in small spots on the bottom of the paper and another solvent is soaked up the paper. Usually this might be water. The solutes present in the dye or the substance that's placed dissolve to different extents. Some are more soluble in the mobile solvent moving up the paper. Others dissolve better in the water trapped in the paper and therefore do not travel very far up the paper. And so this difference of solubility will allow the different pigments in the dye to be separated. One dye can be made up of many different pigments. Like this dye is made up of these three pigments. So, in chromatography, a pure substance shows only one spot on a chromatogram. Chromatography can be tested for other stuff. Like, it can be used to test urine, whether there are some other harmful substances in the urine, some other spots, other pigments that would indicate some sort of disease, and many other things as well. Like, for example, using chromatography, a public analyst can identify the synthetic dyes many foods contain and check that they are harmless. Many green vegetables sold in market have been treated with pesticides and herbicides. These can be harmful to people. Pesticides are used to kill insect pests, and herbicides are used to destroy weeds. So these can be harmful to people. Chromatography can detect such chemicals even down to very low concentrations. So those are different ways paper chromatography is used. But chromatography is also be used to test for purity, how pure a substance is. It is especially useful with complicated chemicals like drugs or food additives which cannot be easily melted or distilled. So, chromatography is used to test how pure they are. So, a pure substance can only show one spot on a chromatogram, only one pigment. Like in this chromatogram here, you can see we have a dye which is X. This has 3 spots on the chromatogram, 3 different pigments. And so this would suggest an impure substance. So is the dye Y. Then we have these 3 dyes. These 3 dyes are all pure. Dye 1 shows only one pigment. Dye 2 also shows only one pigment, so does dye 3. So if a dye shows only one spot on a chromatogram, that would suggest that it is pure. It is not made up of different things. It is a pure, made up of only one substance. So it is a pure dye. In the same way, we can use boiling points to identify if a substance is pure or not. A pure substance has a fixed and exact boiling point, like we read before. The presence of any impurities will raise the boiling point and also cause the liquid to boil over a range of temperatures. We can also test the purity of a substance by the melting point. Any impurities present will lower the melting point, or it will melt over a range of temperatures as it is a mixture. So a pure substance has a fixed and exact melting point, a pure substance has a fixed and exact boiling point, and a pure substance shows only one spot on a chromatogram. So, I hope you've understood this. This was it for the test we use for the methods of purification. Now, in chromatography, we have RF values. Let's look at what these are. It's very simple to understand. RF values indicate whether the solute prefers the stationary or mobile phase. So with stationary and mobile phases, RF values are used to determine polarity, relative masses, and relative solubilities, among other things. So RF values are found using this equation. So finding an RF value of a dye, for example, what we do is that we divide the distance moved by the substance by the distance moved by solvent in the same time. So how much distance has been moved by the substance? We divide that by how much distance the solvent which soaks up the paper in the same time. The distance moved by that solvent. So we divide it and we will get the RF value of that particular substance. So this is how RF values are found. So this was it for today's chapter. I hope you've understood all of it clearly. Methods of purification. In this chapter, we've completed all of these objectives. How to describe the difference between pure substances and mixtures, how to state the effects of impurities on melting and boiling points, and all the other stuff that's written over here that we read in the beginning of this chapter. So, in this chapter, we learned about pure substances and mixtures, the different methods of purification, starting with dissolving, filtering, and evaporating. This is used for separating two solutes, one which is soluble in water and the other which isn't soluble in water. Then we saw crystallization and how microchips are made by crystallization. Then we saw decanting, which means carefully pouring off liquid and leaving the undissolved solid behind. We saw centrifuging. Then we saw the separating funnel, which is used to separate two liquids which do not mix together, which are immiscible. And then we saw sublimation. Sublimation is the process of changing directly from a solid to a gas. So this technique is used to separate substances which sublime from substances which do not sublime. And then we understood simple distillation, which is used to separate a pure liquid from a solution. After this, we understood fractional distillation, which is used to separate two liquids which dissolve in one another. Lastly, we understood paper chromatography, which is used to separate mixtures and which can be used to test for purity of substances as well as detect different substances. We understood that a pure substance has a fixed and exact melting point. It has a fixed and exact boiling point, and a pure substance shows only one spot on a chromatogram. And lastly, we understood the RF value and the equation we use to measure RF values. So this was it for today's chapter. I hope you've understood everything clearly. The next chapter is going to be about the structure of the atom. So thanks for watching, and I'll see you in the next video.